Good afternoon, everybody. Do you have any doubts or any queries from the last two sessions? So if you have any queries, you just on the question tab and then we'll look at it one by one. So proceeding with today's session, so far what we have discussed is the first order system and the second order system, okay, where we did not have any polynomial on the numerator. So let's say the first order system, what we have seen is this one, a second order system. So far we have discussed these two systems, okay? But today we will look into that what will going to happen if I add a polynomial either here or here, okay? Whatever the polynomials or let's say the roots of the polynomials of the denominator, they are called the poles of the transfer function, okay? Or let's say if I write this polynomial by this one, the roots of this equation of the denominator gives me the zeros. So we will look into today that how these zeros affects the response of the system. Okay. So if we take a look at the equation which is displayed on the slides, we have a combination of three polynomials. One is just simple integrator, the second is a first order system, and third is a second order system. So if we club them all together, we get a fourth order system. Okay. And computing the roots of these polynomials, basically there would be four roots because of having a fourth order system. Two roots are located on the real axis and two roots are located on the imaginary axis, which are also called the complex conjugate roots. Okay, so these poles would be, if I write them explicitly, this is for the equation which is displayed on the slides, not here. Okay, so if you see the pole zero map on the real and imaginary axis, this would be, I have a pole, the pole is represented by a cross. I have a pole at minus 1 upon tau 1, and I have two complex conjugate pair, S3 and S4. Okay, so what do you understand? So or first of all, what do you see here, that you have one pole here and one pole here. Okay, so let's say if I remove this pole, if I remove this pole, okay, now I have only one pole here, and I start moving this pole towards in the negative direction. Okay, now I would say cross 1, the new position, cross 2. This is the same pole, only one pole. So what observations will you see in the response of the system? You will notice that as you move farther from the imaginary axis, okay, your response will start becoming faster. Okay, and similarly, the what happen if you start moving in this direction, you will have a pole on the right hand side. It's called the left hand side. This pole give you an unstable system in the sense that your response will tends towards to infinity as t tends to infinity. Yt will tends to infinity as t tends to infinity. But here, if you have a pole on the left hand side, your Yt will converge to some value, let's say some y bar, which is called the steady state value, as t tends to infinity. So we observe two behavior. When I start moving the pole in this direction, if you start moving the pole in this direction, your response will become faster. If you start moving your pole in this direction, your system will become unstable. And here at 0, we have seen already it is an integrating system and it is critically stable system. Is the story if you have a pole just on the real axis, what will happen or what is the response you will going to see for these poles? For these poles which are just on the imaginary axis, first of all, they occur only in complex as a pair. Okay, as a pair, they will occur in the system. And when these poles are on the imaginary axis, you will see an oscillatory behavior. This pole on the real axis will show you the exponential behavior, either exponential reaching to this point, having an initial condition at this point, it will go like this. Okay, this is called the exponential behavior. This is what said in the very first session that the linear system always exhibit an exponential behavior. Okay, about the unstable system, the response will go like this. Okay, for this thing or for these poles on the imaginary axis, I will have some oscillatory behavior, and if they are mixed with the real poles, it will have a damping effect. It will have first of all the oscillatory behavior plus the decaying behavior. Okay, now coming on to the lead lag system, what we will do now, we will consider the first order system and then add a 0 to it. This is my first order system. Now I add a 0. Okay, and this is my transfer function ys over us, and this is also called a lead lag system. The lag behavior you observe because of this pole, and the lead behavior you observe because of the because of this 0. How dominant are they? It depends on the values they take. Okay, so let's say if I start computing the time domain signal for this transfer function for a unit step input, I would have, let's do first the partial fraction. Where a naught is given by this, which I denote by rho, and a1 will be given by, which is denoted by 1 minus rho. So if I write it in terms of rho, I will get okay. So what do you observe here? It is just a summation of two system, or I would say a weighted average of two system where I have a pure gain system. This is called a pure gain. Okay, and this is called of course the first order system. So it is a weighted average of the pure gain system and the first order system. Proceeding it further with this last equation, I could write it. So I take the Laplace inverse of this pure gain system and also the first order system, and I could write in terms of time domain signal. where your YGS is KUS and Y first order system is okay. The Laplace inverse of this one will give me YGT equal to K, YIT will give me okay. So this is what written in the slides. The final equation y of t. If I just put these into this equation, I will get this one. Okay. So now there is one interesting point. Notice that from where did we begin is by starting with this transfer function. Okay. We pre-assume that z and tau are having a different value. What will happen if z is equal to tau? Hmm? There would be polynomials would be cancelled out, and this is what you call pole zero cancellation. Okay, you need to be very careful with this pole zero cancellation while designing your control system, because inherently what you are doing, you are hiding the dynamics of your system from the controller to know that what the process is actually. Okay, so you need to be just careful in designing that if there is a pole zero cancellation, first of all there should not be a pole zero cancellation. Okay, and if it is being cancelled out by the controller, then how you will deal with that situation so that the system dynamics are not hidden by the controller. Okay, so there's some important points. Say at t is equal to 0 plus yt is just equal to k rho. You can observe here, if you put the limit t tends to 0 plus, what will happen? This will go to 0 and this one will cancel out and you will have this k rho only. So this is what you call a jump. That is at t is equal to 0, I will call it t is equal to 0 plus. You observe a jump in the response of the system. You apply a step input. This is my step input. Okay, and suddenly you see a jump here at this position, and then okay, it may die out. So you also need to be careful, because this is happening at t is equal to 0. When your process is running from the past time, okay, this scenario might not be at 0. This might be at some other point. Okay, we need to take care of this jump. This is also called jump discontinuity. Okay, no doubt when t tends to infinity, since this is a stable system, your the response of the system will converge to a steady state value which is given by k. Okay, okay, there are some other points also, that such an instantaneous step response, even denominator polynomials have the same order. So here you, because here we have the same order of the system, 1 and 1. Normally in such system you observe a jump. Okay, so what will happen if I add another pole, this one like this? Okay, there might not be a jump here. Okay. Uh, Now coming on to the higher order systems. So first of all, what do you mean by higher order? So such higher order system can generally be represented in this form, where you have a transfer function, the steady state gain k. This is q in the subscript. Okay. And in the compact form, you could also represent them by okay. So such higher order system are also called PQ order system. Where P defines the order of the denominator and Q denotes the order of the numerator. Okay. So if I look at this equation, K is the steady state gain. Of course, if there are P, if the order of the system is P, I will have P poles, P poles located at where I varies from 1 to P. And similarly, I will have Q zeros located at -1 upon Zi, where I is equal to 1 to Q. Okay. So the transfer function which is displayed on the slides, since it has two poles and one zeros, it is also called a 2, 1 order system. Okay. So now there are some interesting facts about that what could be the values of Q and P. So there could be three cases which could occur. Case 1, that the value of Q is less than P. Case 2, where the value of Q is equal to P. Case 3, Q is greater than P. So when you have the Q less than P, it is called a strictly proper system. Okay. When you have this condition where Q is equal to P, you have you call them either semi proper or high proper systems. And these and in these two cases, we call that the system is physically realizable, in the sense that only this system can be implemented physically. This case cannot be implemented because here you will have more zeros than the poles. Or this system is called non-proper system. Okay. Now coming on to the lower order system, which is also displayed on the slides, a 2 comma 1 order system, and this system is given by, so I need to compute a unit step response. This would become, and US is this one by S. So if I do the partial fraction of this above equation, I will have, okay. So if you compute this A0, A1, A2 by yourself, these values will be, okay. And finally, the time domain signal would be y of t, okay. Now since we are dealing with just the variables, there must be occurring some cases as well, depending on the values of tau, tau1, tau2, and z. So first of all, let's assume let's assume that tau1 is less than tau2. This is my assumption one. Now based on this assumptions, there would be different cases occurring based on the time domain signal we wrote on the right hand side on this equation. Okay. So the case one, that xi1 is greater than tau2. Xi1 is greater than tau2. Case 2, xi1 is equal to either tau2 or tau1. Case 3, xi1 is greater than 0 and tau greater than xi1. Okay. Let's write the transfer function to see it more clearly. I know that tau1 is less than tau2. What will happen if z1 is less than tau2? So in this scenario, if you put this condition into this one, if you put this case into this equation and you plot, you will see that the response will overshoot. If you put this condition that xi1 is either tau2 or tau1, what will happen? There will occur a pole zero cancellation. Okay, we call it pole zero cancellation. And for this one, the response overshoot here. Why? because this is more dominant. The 0 is more dominant than the pole. Here, the third case, where the poles are more dominant. Okay, so here you will not see any overshoot, no overshoot, and the response, if you put this condition into that time domain equation, you will see that the response of the system will resemble a first order system response. Okay, so now there could occur a fourth case as well, where psi is less than 0. What will happen? You see, what you have just done by considering this case 4, or let's see it more clearly on the pole 0 map. This is the imaginary axis and this is the real axis. Okay, this is my pole with this condition tau 1 is less than tau 2. So this one would be tau 1. Uh, Sorry, this would be my tau 2. This would be my tau 1, the pole. Okay, now by this condition, or by this case 4, where xi 1 is less than 0, I would have a 0 at somewhere. You move the 0 on the right hand side, which is very problematic, because what we have seen, whatever moves on the right hand side will create problem, in the sense your system might become unstable. Okay, but the stability is generally governed by just the poles of the system. Then how the 0 plays a role to compute, to determine the stability? No, this question must be coming into your mind. Since the poles just govern the stability, what will happen if I move my 0 on the right hand side? The system will still going to be stable. No, so this scenario is called, so if you put this condition into that yt signal, you will get a response which is called an inverse response. Okay, we will see now what impulse response means. Want to design a controller open loop plant, you need to give this information to the controller that first the system will go in a negative direction, then possibly it will go to the direction where you want it to. We will see it, why this is, what are the more the extra effects of this inverse response. But first we analyze a time the unit step response of these inverse systems. So for unit step response, first I see what will happen at steady state. Okay, this is what I mean by the steady state. That when t times infinity, what will be the value of y? Since the ultimate value of this transfer function would be k1, and for this k1 minus k. So by meaning of this, at steady state, draw the curve before proceeding further. Depending on the values of k1 and k2, the ultimate steady state either would be in the positive direction or either in the negative direction. This condition, this will occur if k1 is greater than k2, and this will occur if k2 is greater than k1. So you see the effect, that I start at this point 0, and finally it reaches to in the negative, for the negative values. Now see the initial slope. The initial slope will be computed by differentiating the response, the overall response is nothing but given by this equation. Okay, and The differentiation of the first order system we have already seen. So writing the final expression, I would get this would be k1 over tau 1 minus k2 over tau 2. So what information is given by this equation? Of course, once again there would be two different conditions based on the values of k1, tau 1, k2 and tau 2. Now suppose I have k2 over tau 2 greater than k1 over tau 1. Think what will going to happen if I have this condition? That you will see that the net initial slope, this is nothing but just the slope, right? The initial slope of the overall system response given by this yt, if I compute it, will be what? Negative initial slope. That the system will move firstly in the wrong direction. So you see, this is what I've been trying to explain to you. What do you mean by the negative initial slope, the positive initial slope, and the positive negative steady state values? So this is here the inverse response comes into play. That let's assume that if the final if the final state value is negative, okay, oh, sorry, it's negative, is negative for the inverse response system, it will go first in the wrong direction because of this positive initial slope. Then it will reach to the steady state value. Okay, similarly happen for this case. So now we can write the conditions, that under which conditions I will observe the inverse response. Let's simplify this transfer function to make it. I'm just simplifying it so that we can observe quickly that will going to happen and from where the zeros appears in this system. Okay, I could simplify it more by just representing it in the form of 2 comma 1 order system. Okay, where this k is k1 minus k2 and this z is given by okay. So now for inverse response, these are the conditions that your k1 and k2 both are positive. Okay, second, k1 is greater than k2, and finally the third one is k2 over tau 2 is greater than over tau 1. If if all these conditions are satisfied, then you will see an inverse response. And if I club them all up, it eventually means that your k is greater than 0, this k, and your z is less than 0. which is equivalent to say that you have the right half plane zeros. So let's consider a physical process where you generally observe this inverse response. That consider the system where you have a feed water pump, okay, which is controlled by a valve, okay. Now you have a boiler drum which is used to boil the water and produce the steam. Here you will have some vapor bubbles also, and here you take the steam out. So representing it a simple process, this is the input. Let's say I call this the input of the system, and this is my output, y of x or y of t. Okay. Generally, in such kind of system, you observe an inverse response. Why? Or maybe I will show you with in the next slide. Okay, where I plot the response. The green line in the figure shows this green line shows that this is the set point. Okay, this is the set point from the controller point of view that you need to maintain a desired level in the boiler at this value. Okay, and the red one is the control variable which you manipulate so that the liquid level in the boiler could stay at the set point value. And the blue one is basically the measurement, the output. Okay, since the system is in operation, if you give a constant u from here to here, you will see, or the controller was whatever the controller has been designed, the measurement was actually following the set point. Now try to think analytically or logically that once you increase the level of water or you make a step change here, you make a step change so that more water could flow in the boiler. Okay, of course the steam would definitely would go down, and then the controller will see, okay, the steam is not matching to the set point. It will start putting more efforts so that it will start tracking the set points. In that doing so, possibly it could occur that the response will go much faster, and finally it will settle down at the set point value. You see, and this is what I call, or where do you see the inverse response? And you see, and you notice that what way, that once you have make a step change, okay, once you make a step change, this output start increasing instead of tracking the set point. Why? Because the controller gets the information that if you put more energy, okay, the system will go in the negative direction, so he needs to make more efforts. So this is where you basically see the inverse response in the physical processes. Some effects of additional poles and zeros. I've written feed transfer function which is generated by system A, system B, and system C. In system A, you will notice that I have 2 poles and 1 zero in the negative direction, which for sure will going to give me inverse response. In system B, I have 3 poles and 1 zero, and system C, I have 3 poles and 2 zeros. So what we have observed in the previous sessions, that adding a pole to a system basically slows the response. So this is the difference you will notice in system A and system B, because the difference in system B is an additional pole, except that the whole system A is still there. So if I add just a pole to system A, the response become a bit slower. Similarly for system C and system B, in system C what I did, I add a zero, which is going to say I speeded the response. So the system, here is the system C and here is system B. The response of system C is speed up in comparison to system B. Okay, and the difference between system A and system C is that one additional pole is there and one additional zero is there, and depending on the values of these poles and zeros, system C responds slowly, because here you will see the pole is quite dominant than the zero. Okay, so these are just some comparison to let you know that what effects will going to appear in the response of the system after adding an additional poles and zeros. Okay, in this slide you will see the difference in the inverse responses, that here for this system I have only one, it only once time it goes into the negative direction. Here it goes two times, here it goes even three times depending on the poles. I will let these slides to study by yourself. If you study these two rules, you will see or you will notice that how many inversion will going to appear. Now the next topic is the time delay system. Okay, I will make a pause here just to gear up yourself for the new topic. And in the meantime, I will give you one problem to analyze by yourself. I can write this problem onto the board. This is problem 5 from the assignment, where the system transfer function is given by this one, but with having a delay. We will discuss this after the break, that what effect does it make to the response. So you need to put this system in the standard gain time constant form. Okay, and determine the poles, zeros, and the gain of the system. Okay. Okay, so the problem was given from the assignment. This problem, as you can see, that the problem is number 5, where only the A B part is asked you to solve. So in the first one, you need to put this system into a standard gain time constant form. Okay, and the second one, you need to determine the pole, zeros, and gain of the system. So I will not going to solve this for you. That how can you put this into the standard gain time constant form? But I would rather be interested, you know, in doing the that what effects this exponential factor will bring into the response of the system. Okay, so now moving further with the time delay system. By the way, as just a hint to the previous problem, you will notice that there is a pole zero cancellation. Okay, if you try to that transform into the standard form. Okay, so what do you understand by a time delay system? So time delay system are generally very you will see in almost every processes, because at least in the chemical process industry, there you have a large pipes where the input goes from one end to another point, which is also you could see in this slide, that the input or the liquid is flowing point to another point, and it will take some time. Of course it will take some time, and this is what you call the transportation lag or the transportation delay. So we will see that how you model this thing and what are the effects of this system of this time delay. So this transportation delay between point 1 and point 2, you can denote it by theta, which is the length of the pipe over fluid velocity. Okay, this is the basic equation of the flow of the liquid. Okay, let me finish with this, the brief introduction about the time delay system, then I will come on to your questions. Okay, you could also write it that the volume of pipe over volumetric flow rate. So if I want to model the system, let's say that absolute property at point 1 is denoted by x, okay, and the same property at point 2 is denoted by y. Then what is the relationship between the x and y? This relationship is given by y of t, that it is 0 for t less than theta, and it is then given by this expression t is greater than equal to theta. So you will see that at theta is equal to 0, okay, which is going to say that you are at point 1, yt is equal to xt, and when t is greater than theta, the more you go, the more delay you will observe. So now how I can determine the transfer function of the system? So what I will do, take the Laplace transform, is given by ys over x's equal g of s e to the power minus theta s. This is the property of the Laplace transform. You could also write this 1 over e to the power theta s. This is a different transfer function from what we have been considering so far. It is not either a first order system, neither a second order system, okay, and we don't know either we will going to consider it as a zero, just a zero, or just a pole. So what we'll do, we'll take the Taylor series expansion of this e to the power theta s, and this will give me, okay, which is infinite of course. So what you will observe, that it is an infinite order system, will have infinite poles. So considering this equation, we will note one interesting point here. Consider, I will let this equation to write over there, and let's see, I take an first order system in series, okay, what it will be, I could gn of s, okay, where this term is my tau, okay, so it is nothing but just n first order system in series, okay. So what will happen if, when n tends to infinity, I take the limit n tends to infinity, e n of s, okay. Now try to recall your first year engineering mathematics, that your exponential term is defined by, and if I take the power of minus alpha, it would give me, okay, and I could write it also in this way, okay. Now let n is equal to alpha m, then it would be e to the power minus alpha limit n tends to infinity this thing, which is equivalent to say that is limit n tends to infinity g of n s is nothing but equal to e to power minus alpha s. So what do you notice from this point? That if you put n first order system in series, it is nothing but a delayed system. You delay system by the transportation lag bar. So it brings to us to the basic fact what we are discussing, that whenever you add a pole to a system, you are slowing down the response and you are delaying a system a bit. But as you add infinite number of first order system in series, it's an infinite delay. But while designing a control system, okay, we usually do not, it is difficult to analyze, okay, and what we have been so looking so far, either the first order system or the second order system, or we try to limit ourselves to get up either, or even if it is a higher order system, we can approximate either to a first order system or second order system, so that we can design a control system accordingly. But since you have a delay in your system, what we have seen, it brings us to an infinite order system. So we need to approximate it to a lower order, and we'll see how. But before moving further, I'll take some couple of questions. Okay, if system gain k is negative, what should be inferred about the system? If the system gain is negative, in which system? I suppose that you are asking this question assuming that you have a 2 comma 1 order system. Okay, the system gain basically defines the steady state gain. Okay, so if I draw a simple figure here, okay, what we have been saying, if there's a negative, first of all it depends on the system. Let's write from the scratch, uh, that you have a system for the first order system. Okay, this is the first order system. Okay, this is the first order system. Okay, if the gain is positive, the steady state gain is k is positive, you will have this, you have the response of the system in this way, for k greater than 0. You will observe this response k is less than 0. There is nothing but just the steady state gain, and this is the impact, or I won't say the impact. It is, it would be a property of the system that the gain is either negative or positive. Okay. Hello, SRTC.
Hello. Yes, sir.
Yes.
Yes, sir. CT here.
Yes, I can hear you. Please ask a
Hello.
question.
Why first order and second order system
Can you
considered
hear
for
me?
the analysis? Why first order and second order system only for considered for analysis? What about higher order? Hello.
For analysis. Why? So this is what I was discussing here, that generally we want our system, whatever, first of all, why you have to understand that why we are analyzing the system, because our final aim is to design a controller, and the controller needs to have a simple model of the, okay, and if we,
Okay.
and like I said, that we can approximate the higher order system to first order and second order system, then we have an ease to design a control system. Okay, like the case we have here, if you consider a time system, it is an infinite order system. Okay, I cannot design a controller for this. I need to approximate it either to first order or a second order system, so that it gives me an ease to design a control system. Okay, this is why we generally
Okay.
trick
Thank
ourselves
you.
to first order or second
Thank you,
order
sir.
system. Are there more questions from KSRCT? Okay, so where were we? We were at the uh, approximation. How I can approximate. Hello, Amrita TN.
Sir, my name is
Yes,
Satvik. I want to know some examples where the system has negative gain. Can you explain?
the system
Can you
has
say
negative
some
gain.
examples? Yes.
The practical where system has negative gain.
It's a practical.
The practical system you mean to say?
Sir, some examples for the system which has negative gain, practical systems.
Okay, and what is would be your final aim? Because like I said, it is an inherent property. Like I said, it is an inherent property of the system that it could either have a positive gain or a negative gain.
Negative
Okay,
gains.
but yeah. But what you would finally would like to do with that gain? Either you want to design a controller for that system such that it maintain at its negative position, or
Negative
you
position.
want that system to go into the positive direction because of the controller.
No, it's negative direction. Negative direction. Inverse. Examples. Sir.
So the examples,
Yes, sir.
mm, well, basically just an inherent property of the system. So possibly the example is, or maybe you could consider this absorber system. Let me open this slide. That would be, I think, the perfect example. Yes, NMIMS. Okay. So now we consider a first order plus time delay system. That what this delayed system comes into the appears in the first order system what we have been considering, and this system is given by, okay. So from where do you obtain, or how do you obtain this first order plus time delay system? Consider this example where I have a measuring device. It is the basic reactor what we have been considering from the very beginning. Okay, forget about this concentration controller now. Just think this system as an input from here and the output from here, and this is the input to the reactor. Okay, this is the input. So there's a relationship between I and IR. Why? Because of this long pipe which adds the transportation delay. Okay, we have seen from the previous sessions that this system can be approximated by a first order system, and this W is here, this Y is here, and this delayed is being added here into the overall input given to the system. So when I combine this overall system, I get a first order plus time delay system, where this is a first order system and this is a delayed system. Okay. So now how I will going to approximate this FOPDD system, either with this one by one paid approximation or with this Taylor expansion. We'll see the case of Taylor expansion first. Okay, I will write here. So with neglecting the higher terms from here, okay, I could approximate this e to the minus theta s by this quantity only. So it would become this one. But is this the only possibility? Because here what you are doing, you are adding a right hand part 0. Okay. Another possibility, I could write this transfer function as this one, and this would give me, which is better? Adding a 0, a right hand part 0, or a pole, a left hand side pole. By the way, did you notice one thing here, that if you have a first order system, this is already a small or a lower order system. Okay, even if we have a higher order system, I can approximate to this system by this property. You see, so this is also another way to approximate higher order transfer function in terms order plus time delay systems. So we'll see how. Okay, so as you see in the slides, what I have done, I take the unit step response. There are two transfer function given are plotted in the figure, G1 and 2, and this is G1 and D2. If I take the 1 by 1 paid approximation, and if I take the 2 by 2 paid approximation. So if I plot this curves to this unit response, this is the actual response. Okay, this is if I take the 1 by 1 paid approximation, and this is if I take the 2 by 2. So as I proceed taking the higher order paid approximation, I will be getting close to my actual response. This is also being displayed here on the first order plus time delay, that this is the exact response, and these are the G2 response if I include these terms into the final first order plus time delay system. Okay, this is called the approximation of higher order transfer function. Like I was saying, that if you have a higher order transfer function which is given here, that you have 3 poles and 1 zeros, then how you could approximate to a FOPDT system? There are two rules. Either you do by Taylor series expansion like we saw here, and there's another rule called Skogestad half rule. So we'll see now how these two rules works. But okay, is any system positive gain the time domain and negative gain the frequency domain? What do you mean by this? Uh, I'm trying to understand your problem, that what you really wanted to ask. If you write a more clear question, then possibly, sir. Because first of all, you need to understand that whatever the transfer functions we have considered here, they are frequency. Now, when we have seen in the very first session the interrelationship between all the representation of the system, there we have the transfer function, state space, impulse response, and the frequency response. And this transfer function is nothing but basically the frequency response which we use to do the time domain analysis. So seeing this transfer function, that how I can approximate this higher order transfer function to a FOPDT system. Okay, so the Taylor series expansion rule says, okay, retain the dominant time constant, and among these time constants, let's say I call it tau 1, tau 2, and tau 3. Tau 3 is the most dominant one. Why? Because of, okay, and approx rest of the transfer functions or the polynomials. So I would retain this one. For this one, I could write it e to the power minus 0.1 s. Okay. For this one, I could write this, and if I club them all together, or this one. Okay. This is the Taylor expansion rule. Just let them see this thing. What is this function? Does the order of the system affects the stability? Not basically. Why it should be? Why it should affect the stability? When we consider the stability, if we have a negative, if we have the left right hand side poles in the transfer function, then and then only it affects the stability, in the sense that your system will become unstable. Okay, so the order of the system does not affect the stability in the usual sense that your system will turn into an unstable system. So this is called the Taylor series approximated transfer function. Hmm? Okay, yes, if it is possible. A higher value of time delay, that once you, it is almost similar, it is almost similar procedure you will follow whatever we have done for the first order and second order system, that you need to approximate it to lower order one. Then either you could, like I said, either you could use the lower one by one paired approximation where you add 1 0 or 1 pole. Okay, and then you start doing your analysis in the same way we have done for the first order and second order and pole lead lag systems. Okay,
Good evening, sir.
good evening.
Sir, this is Akash Prasad, and I'm from NMIMS Shirpur. So my question is to be asked that is there a system which has positive gain in time domain or negative gain in frequency domain?
It is the one. What do you, first of all, what do you understand by the steady state,
Well, just
steady
I'm
state
asking
gain?
that
Because
for us.
state, uh, let me complete. Because the steady
Yes,
state
sir.
gain
Yes, sir.
basically gives you that what will going to happen at time t is equal, when time t tends to infinity. Okay, it is an inherent property of the transfer function. Either you do the time domain analysis or the frequency domain analysis, the things will going to remain the same.
Okay. So
See,
the second question is to be asked that is the order of the system affects the stability?
in which sense?
So, like, if the higher order systems, if we are considering the higher order system, we are studying for the second order system and first order system. So, what do
Hmm.
you think that the second order system is much more stable than the first order system?
No, you cannot say this straight away.
So then, can you elaborate your
Okay,
point?
like I said, the stability of the system is governed by the location of the poles and zeros. Okay, if if your any of the pole is on the right hand side, okay, then your system will is an unstable system. Until your all the poles remain on the left hand side, your system will going to be stable, no mattering what is the order of the system. You see,
Okay.
if you do not confuse, because what I'm sensing that you are confused with the stability and the speed of the speed of the response.
Yeah, maybe.
The speed of the response will be affected for sure. Okay, but until you are adding a left hand part poles to make it a high order system, okay, the stability won't be affected.
Okay. Okay. Thank you, sir, for your time.
Okay, so looking quickly that what does this suggested half rule says, we are taking the same transfer function. Okay, so this rule also says approximates the largest neglected time constant. So this time constant will going to stay in the first FOPDT system. Okay, the largest neglected time delay is this one now, tau t. Okay, so 1/2 of its value is added to the existing time delay. Okay, so from the first point, I will take the half of this one, which is 1.5, and will add to the existing time delay, which will give me 6.5. Okay. So now writing the square half rule transfer function, A would going to remain the same. With this time constant, I will have a transfer function, this one. This is 6.5 s plus 1. Now the rest thing is this, what I will going to put it here. Okay. Second says, other half is added to the smallest retained time constant. So once again, I take the half, I add this to the smallest one, which give me 2. The third time constant that are smaller than the largest neglected time constant are approximated as time delay using the previous equation what we have seen earlier. So if I sum them all the transfer function, I would have 1.5, 0.5 and this one 0.1 plus 0.1, which would give me 2.1. The delay, though my transfer function will become this one. This is the approximation of this transfer function using two rules. One is Taylor series expansion and another one is Cogister half rule. So if you see, look into the slides. Okay, if you look into the slides, the Cogister approximation matches closely to the actual response instead of the Taylor series. Okay, so there's just a difference to show you that if you approximate the advantage of one rule over the other. Okay, so now we can take some questions. Okay, the it says, which are the new control system softwares? What do you mean by the new control system softwares? First of all, it depends that for which application you would like to use. Okay, if you just want to use this, or let's say the control system software for research and development purposes, normally we use MATLAB or LabVIEW. But since LabVIEW is more industrial friendly, so in industries people generally use LabVIEWs. You can also implement your control algorithms either using this PLC codes. Okay, this is one way. How to realize time domain analysis in MATLAB? Okay, for this, so I don't have the MATLAB with me right now, because if you see, if you have downloaded the assignment, the sixth question asks you to solve it in MATLAB. Okay, so in MATLAB there is a toolbox called control system toolbox. Okay, there's a help file also in the guide. So because also I wrote some codes on the slides for plotting the step input, impulse input and rectangular pulses. So what you need to do, so if I take a very basic example just to start so that you can start up. So let's say if I want to implement, or if I want to see the step response, okay, of a system given by 2 by 3s plus 1. Okay, and this is how you input in the MATLAB. I take the numerator polynomials and denominator polynomials separately. Okay, I take this. This basically defines the, because everything whatever you put in the MATLAB is in the form of a matrix, and this defines the order or a vector basically. And then you make a transfer function by this command called TF. Okay, then if you do not put this semicolon, okay, you will see this transfer function. Okay, and if you, because this is the inbuilt command in the MATLAB, if you put just the step of G, you will the one window will pop up with the figure that how the step response will looks like. Okay, and similarly you could do this for for the other inputs for which the codes are already mentioned in the on the lecture slides. Okay, can you please explain frequency response analysis with a practical example? Well, we we have now very short time to start with the frequency response analysis, because whatever we have covered so far is based on what you do in the time domain. For the frequency response, of course, I need to go into the root locus and the Bode plot to, to see the effects of what the poles and zeros make into the response of the system. Okay, so I'm sorry that we cannot cover this frequency response now. Okay, do we have huh? Where? This is what I explained here.
So is transport delay accounted for systems only in process industries?
No, of course not. This is one
Uh,
example I considered. The
so,
transport delay, uh, like in the transport delay can occur also in other systems as well.
sir, couldn't get you.
Okay, it depends on the kind of actuators you are using, and right now I don't have an example in my mind, but possibly, in fact, the flow of electrons, okay, can also be considered as the transportation delay. Okay, whenever you consider any electronic system. Okay,
Okay, sir. Yes, sir. Thank you, sir.
okay.
Hello, sir. This is Sudakshan. Can I actually handle a sixth order system as three second order systems?
You can do what?
Handle a sixth order system as three independent second order systems.
As three independent second order system. In what manner? Because you can consider three system either in series. Okay,
In series, sir.
so let's say if you have a sixth order system, okay, and you make three blocks, okay, a second order system, a second order system, a second order system. Is this what you want to ask?
Yes, sir. Is can we implement this?
Yes, you can implement this. You can implement this. Okay, doing the analysis and designing a controller for this one, okay, it's a separate story. You
Will
can
this
of
be
course
better, or
implement this.
six first order systems? Splitting it as six
It
first order
doesn't, it's
system.
the
Will
same
that
thing.
be better?
Basically, it doesn't matter. It is the same thing that either you put six first order system or you put three second order system. You see? Okay. So we are done with this topic one. Thank you for attending the classes. Thank you for now. you.